So today we will discuss about design of springs, right? So actually first let us see what is a spring, right? Then we will see these types of springs. So basically spring is an elastic machine element, right, which is going to deflect under any load applied, and it is going to regain its original shape when the load is removed, right? So we can first define spring as an elastic machine element right, which is going to deflects under the action of load, right, and it is going to regain its original shape. When the load is removed. Now springs are used for various applications, right? So some of them are to absorb shocks and vibration. Right, in vehicle suspension this spring is used, right? Shocks and vibrations. Right, it's also used to store the energy. Right, it can be used to measure force in weight balance. You must have find the spring, right? Used to measure force. And it's sometimes also used to apply force, like in cam and follower mechanism we are using spring, right, to apply this force so that contact remains between cam and follower, right? So there are various application of this spring, and generally various types of springs, but these helical springs are most widely used, right? So in helical springs also there are various types of spring. As you can see in this given figure, compression spring and extension spring is there, right? So compression spring means when the load is going to be applied on this particular spring, it is going to get compressed, right? So its length is going to decrease. Similarly, in this extension spring, whenever load is going to be applied on this spring, it is going to expand, as it is shown in this figure. But here compression and extension is basically the things which are happening to the length of spring, right? So the spring is not experiencing any tensile or compressive stress in this case, right? Here spring is not under any tensile or compressive stress, right? Here in this particular helical springs, when load is applied, there is the spring is under torsional shear stress, right? So that we need to keep in mind, right? Here torsional shear stress, right? While if we go for this helical torsion spring or this leaf spring also you may have seen in the trucks and all suspension system. So here in both this case the spring element is going to experience bending stress actually, right? This master leaf of this leaf spring or this particular helical torsion spring is going to experience bending stress. So this is how the different types of springs and the nature of stress experienced by these different types of spring is there, right? So now if we go for terminology of helical spring particular case, if we discuss, then as you can see in this figure, here various parameters are mentioned, right? If we start with this small d, then this small d is nothing but the wire diameter of spring, right? This is wire diameter of spring. Similarly, this di and du are inside and outside diameter of spring coil, right? Here di and du are inside and outside diameter of spring coil. Right, while this capital D here, as it is mentioned, this is nothing but mean coil diameter. Right, as it is the name suggests, you can calculate it with this di plus du by 2. So this is how this length terminology we will discuss in the next slide at length, right? How these different types of lengths are considered in spring, right? So these are some of the basic terms related to this helical spring, right? And when we discuss about helical spring, then one important term defined is this C, which is also known as spring index, right, which is actually given by this capital D by small d. And we have defined what is capital D and small d, right? It is mean coil diameter, right? And this is this wire diameter of spring, right? So generally based on this value of this capital C, you can check how sharp your spring will be, right? If this C is less than 3, then there will be very sharp curvature and it is very difficult to manufacture, right, type of this spring. So generally this C is kept between 4 to 12, right? So this is how you are having these various terms related to your this helical spring. Right, now if we go for this spring length terminology, then here we are having three different keys, right? One is this solid length, then compressed length, and free length. So if we go one by one, then first if we discuss this solid length, then as you can see in the given figure, when force is applied in such a manner that each this coil is in contact with another coil, right, as you can see in this given figure. So solid length is basically given by this nt into d, right, where nt is nothing but this total number of this coil turn, right, and this d is, as you know, this coil diameter. So solid length is given by this nt into d. Now in case of this particular compressed length, your spring is compressed at its fullest capacity, right, whatever maximum load it can bear, right, as it is mentioned here. So at this maximum load, whatever is the state of this particular spring is known as this compressed length. In case of this compressed length, you are having a particular gap between this two coils as shown in the figure, right? So this total gap is actually given by, in case of this compressed length, we need to have idea about this total gap. So this total gap is actually given by this nt minus 1 into gap between adjacent coil. Right, so this is how it is defined in case of this compressed length. And as you can see, so compressed length, this delta is also included in this compressed length, right? So basically this compressed length is equal to this solid length plus gap plus delta, you can mention like that, right? So sorry, if you include that delta, then it will be free length, right? So compressed length is basically this solid length plus this gap, that is compressed length as it is mentioned here, right? So one second. Yeah, so here in case of this particular length terminology, the final thing is this free length, right? So free length is, as just now I have told you, right, this free length can be represented as a compressed length plus delta. As you can see here, this is compressed length mentioned and this is delta. So compressed length plus delta can be your free length, right? So apart from that, it can also be represented, or this free length can also be represented with the solid length plus delta plus total gap, right? As we have defined this gap, right? So total gap. So free length can be calculated with this. Apart from this length, here we can also define this pitch as it is mentioned here, this P. So P can be defined as, in case of free length only we are defining that pitch. So it is free length divided by nt minus 1, right? So this is how we are having this particular things related to this helical spring. Now if we go further.
Excuse me, sir.
Yes.
Please, can you explain that total gap is equal to nt minus 1 into gap between adjacent coils?
See, in case of total gap, as you can see here in this figure B, right, total number of this coil or total number of turn, right, it will be the total number of turn minus 1 into this gap, right? Because whatever total number of turn we are having at the beginning, it will start with this, if you number this turn, right, 1 2 3 4 and so on. So up to here, if you see, what will be the gap? It will be this 4 minus 1 into this gap, right? 1 2 and 3. So for example, I have explained here, it will be nt minus 1 into the gap between adjacent coil. Are you getting?
Yes, sir.
Right. So like this you can define it, right? Now here, in case of this helical compression spring specifically, there are active and inactive coil, right? Because what is active and inactive coil? Let us see. In case of this helical compression spring specifically, what happens is each coil does not take part or undergo deflection during application of load, right? So what happens is, if you apply load, right, as here it is shown in this compression spring, right, if you apply load here, right, it may happen that this some of the initial particular turn does not undergo any deflection. It will remain as it is. So those particular those particular inactive or those particular turn which are not taking part in deflection are termed as inactive coils, right? So inactive coils can be calculated with this nt minus n. This is total coil, right? Minus n, right? And n is what? Nothing but active coil. So this also you have to keep in mind, that what are the number of coils taking part in deflection when the load is being applied. Now in case of spring, one more important term is stiffness, right? So this stiffness is nothing but load per unit deflection. Right, so these are some of the basic terms and terminology related to this helical spring. Right. So now if we go for this style of end, as we have just now discussed, in case of this particular helical compression spring, there are different types of end, right? So this table belongs to this helical compression spring, and in that case this number of active turn is defined, as we have just now discussed active turns and inactive turns, right? So here this plane and ground end, similarly square ends and square and ground end, and how the number of active turns are calculated in those particular case is mentioned in this table, right? And in case of this helical extension spring, your total active turns are total number of turns only, because in that you are not having those inactive turns as in case of this helical compression spring. So and various types of end style for helical extension spring are also mentioned in this particular figure, right? So this is how we are having this helical compression spring and helical extension springs ends, right? Now if we go for this stress and deflection in case of this helical spring, so as it is mentioned in this particular case, figure A shows this helical spring and figure B shows that unbent helical spring as it is mentioned here, right? So now if you look at the force applied here, right, this force P is applied at a distance of d by 2. So by looking at this particular figure, you can simply write the torsional moment mt equal to that load applied into the distance, right? So once you have torsional moment with you, then from the theory of pure torsion you know how stress is related to this torsional moment, right? This stress can be given by this 16 times this t upon pi d cube. You know, right, from where it has come. It has come from this tau upon y is equal to t upon j, right, is equal to this g theta by l, right? So this is theory of pure torsion, right?
Yes, sir.
So from this you can calculate that what is the shear stress developed because of this torsional moment, right? So now if you simplify this, put the value of that mt, then you can get it as 8 pd upon pi d cube. So you know, right, what is P? That is the load applied. This D is mean coil diameter. This small d is that wire diameter of this spring, right? So this is how you are having the shear stress developed in your spring. But here what we have considered is we have simply unbent the spring. We have not considered the direct shear stress, or we have not considered the stress concentration due to the curvature in this spring. So for that we have to consider some factor, right? That is, let us call those factor as Ks and Kc, right? So Ks is factor to account for direct shear stress, factor to account for direct shear stress. Similarly, this Kc is factor to account for stress concentration due to curvature effect. Right. So by considering both this effect, you can define one more constant, let us say k, right? So which is nothing but this ks into kc, right? So we will see how this particular constant is going to be used, but before that if we consider the direct shear stress itself, direct shear stress acting in this particular case as, let us say, tau 2, then that is nothing but this force divided by area, right? P is equal to, sorry, tau 2 is equal to this load upon area. So if you write this, that 4P upon pi d square. Now if you further simplify it, then you can also write it in terms of this 8PD upon pi d cube 0.5 d by d. So basically here we have multiplied and divided by this capital D and small d, and similarly 2, right? So by multiplying and dividing it by that 2 capital D and small d, you will get it in this form. Why we have done this? Because in order to calculate the total shear stress, we need to add this tau 1 plus tau 2, and as you know, as you already know, that tau 1 we have derived as this 8PD upon pi d cube, right? As you can see here, if you say this as 1, right, and consider this as 2, then you can add both of this 8PD upon pi d cube. So I am not writing it again, I am directly taking it common, so that is 0.5 by C I am writing, right? Because you know C is nothing but capital D by small d, that's spring index. So once you know this total shear stress acting in your spring, then you can derive this particular relation, right? Now this particular whole factor is shear stress concentration factor. Right. Now one scientist has derived that Wall factor, right? That scientist name is Wall, so it is known as that Wall factor. So the C, it can be represented with this 8PD upon pi d cube into this key S, or as Wall has derived one more constant, this is known as Wall factor, right? So here also it is 8PD upon pi d cube. So what he has come up with is his constant is this k can be represented with this 4c minus 1 upon 4c minus 4 plus 0.615 upon c. So this is how you are having this particular shear stress acting in case of a spring. Now up to this point, what you have considered is this shear stress acting on it, right? But what we are interested in is how this particular spring is going under deflection, and what is the stiffness of this spring, right? So that is more important for us, right? So what is important is this deflection, right? What will be the deflection and what will be the stiffness, right? This is more important in case of this spring, right? So
Actually,
yes,
that wall factor and Ks into Kc are the same.
uh, you can consider, right? But this is different actually, means it has calculated based on some experiment, and maybe there's some empirical relation he has found, right? So it is not exactly same, but you can consider it as that particular effect of this curvature as well as effect of this direct shear stress, right? Okay.
So wall factor is derived from the considering the both
Okay.
Yeah, yeah.
curvature and the direct shear stress.
Yes, yes, yes. By considering both. Okay. So now if we are interested in calculating that deflection and the stiffness, then if you look at the figure given here what we are interested in is this delta, right, as we have just now discussed. So if we are interested in this delta, then from this figure you can see that this particular deflection is nothing but the angle of twist into the distance, that is d by 2 radius, right? R theta is this particular arc length delta. So this delta is nothing but this theta into d by 2. So in order to calculate delta, first you have to calculate angle of twist, right, that is theta. And as you know from this theory of pure torsion, here you can have relation between this theta and stress, right? So from that you will be able to calculate theta first. So if we go and calculate the theta first, then theta is nothing but this mt into L divided by G into J, right? So now if you put the values in this particular equation, then you know mt is nothing but p into d by 2, and you know L is nothing but pi d into n, right? Similarly, this J is nothing but pi by 32 d raised to 4, and G is as it is, right? So if you give simplification, then you will come up with this 16 pd square n upon gd raised to 4, right? So this is how you are having your this angle of twist. So now once you have angle of twist, you can calculate the deflection, because deflection is nothing but theta into t by 2, as we have seen from that figure. So theta you have calculated as 16 pd square n by gd raised to 4 into d by 2. So it will give you 8 pd cube n upon gd raised to 4. So this is how you can have your deflection of spring, right? Now once you have deflection of spring, then you can also easily calculate the stiffness, right? This is stiffness. I am writing stiffness because K we are using for some other things also,
Sir,
right? Yes. Huh.
that N was for total number of turns or active coils only?
Active coils only. Okay.
Okay.
Mm-hmm. So this stiffness is this load upon unit deflection, right? So now you can write this P, and what is deflection, that just now we have written, right? Let us see what is the deflection. So it is nothing but P by 8 PD cube n into this GD raised to 4. So basically K is given by this GD raised to 4 upon 8 d cube n. So this is your stiffness, right? So this is how you are having the stiffness as well as deflection. So as you can see, this deflection is proportional to the load applied, right? And from load deflection curve, you can also have idea about the uh, strain energy stored, right? So if you go for load deflection curve, then as load increases, this deflection increases, right? So the strain energy stored can be given by this area, right? And this is right angle triangle, right? So your area is nothing but this 1/2 P into delta. So this is the strain energy stored in your spring. So this is how you are having this various design related equations in case of your design of spring, right? So before going to the numerical, one more important concept in case of spring is this springs in series and parallel. So if you take one by one, if you first go by this spring in series, right, let us say. So as you can see, in case of this spring in series, when you apply load, what is going to happen is the total deflection will be given by the deflection in spring 1 and deflection in spring 2, right? So in order to calculate the equivalent stiffness in case of the springs in series, we can consider that total deflection is due to the total load applied upon the equivalent stiffness, while for this delta 1 will be the load applied upon the stiffness of spring 1, right? Here actually load applied is same in case of series, right? So P will remain same for both the spring. So deflection will be given by P by K1 and P by K2, right? Because stiffness is different for both the springs. So in case of springs in series, your equivalent spring stiffness, if you consider it, then it can be given by this 1 upon K1 plus 1 upon K2, right? And in case of this springs in parallel, as you can see, what happens in this particular parallel spring is load is differently beared by both the springs, right, while the deflection will remain same for both the spring. So if you go for calculating the stiffness or equivalent stiffness, then here delta will remain same, right? So here K1 delta plus K2 delta, because deflection is same in case of springs in parallel. So equivalent spring stiffness can be calculated with this, right? So these are some of the important things you have to keep in mind while uh, designing this spring, right? So once you have this particular idea about the spring, you can try and calculate this numerical. So what this numerical says is, it is required to design a helical compression spring subjected to a maximum force of 1250 Newton. The deflection of the spring corresponding to the maximum force should be approximately 30 mm. Then the spring index can be taken as 6. The spring is made of patented and cold drawn steel wire. The ultimate tensile strength and modulus of rigidity of the spring material are 1090 and 81,370 Newton per mm square respectively. The permissible shear stress for the spring wire should be taken as 50% of the ultimate tensile strength. Now design the spring and calculate wire diameter, mean coil diameter, number of active coils, total number of coils, free length of the spring and pitch of the coil, and draw the neat sketch of the spring showing various dimensions. So now can you try this question? Hello.
Sir, yes, sir.
Okay. So it is a straightforward question, right? So first you need to note down the given data. Here your load is given as 1250 Newton and delta is given as 30 mm. Spring index is given as 6. Then ultimate strength is given as 1090 Newton per mm square. And G is is 81,370 Newton per mm square, and this shear stress you can consider as 0.5 times SUT. Right, so that is nothing but 0.5 times 1090, right? So that is nothing but 545 Newton per mm square. So now first you can calculate the wire diameter, right, as it is asked here, wire diameter. So how can you calculate wire diameter?
From deflection equation.
Here's the formula.
Shear stress formula will give you wire diameter, correct? Because shear stress formula is what? Is tau is equal to K into 8 PC upon pi d cube, right? Sorry, pi d square. Right? This formula will give you the wire diameter.
Five 5.91 mm.
Sorry. First you have to calculate this K, right? Wall factor 4C minus 1 upon 4C minus 4 plus 0.615 upon C. So what is this?
$1.25.
Yeah, it is around 1.25. So once you have calculated this, then you can write the other things which are with you, right? Like tau is 545, then K you have calculated this 1.25, then 8 into that 1250 Newton, right? 8 P into C, that is 6 upon pi d square. Right, so now if you solve this, then it will give you D.
6.61.
Sorry?
6.61 mm.
Yeah, if you consider 6.61, or you can take it as 7 mm. Correct? So this is your wire diameter, right? So from this wire diameter, you can calculate the coil mean diameter, right? By C into this T. Yes or no?
Yes, sir.
Yes, sir.
So it will give you this 42 mm. Now number of active coil, how you can calculate number of active coil?
In the condition of the
Sorry?
Deflection equation.
Yes, because as somebody has asked, this N is active coil, so I told yes, right? So in deflection equation, you are having this 8 PDQ N by GD raised to 4. So you have everything with you in this equation also. If you put the given values, and deflection is given as 30. Right, then 8 into P is given as 1250. Then capital D you have calculated as 42 into N upon GD raised to 4. D you have calculated as 7. So this will give you N.
8.
Yeah, it is 8 almost. 8 coils, right? 7.9 or something you will get. Right, so 8 coils are there. Now total number of coils also they have asked. This is active coil, right? So in case of total coil, if you assume that the spring has square and ground ends, assuming square and ground ends, total number of coils is equal to whatever active coils plus 2, right? So it will give you 10 coils as total number of coil. Now you are also asked to find the free length of coil. So how will you proceed with that? See, after considering here 8 coils, your actual deflection will be different. Yes or no?
Yes, sir.
Correct. So what you are going to do is first you are going to find the actual deflection, because you are also asked to find the free length, right? In case of calculating this free length, what you first need to do is you first need to calculate the actual deflection. So this deflection is what? 8 PD cube N upon GD raised to 4, right? So by considering exact 8 coils, what will be your deflection?
30.34 mm.
Correct. 30.34 mm will be your actual deflection. Now, what will be the solid length of spring? We have seen that relation, right? You know,
N into D.
NT into D, no?
Yes, sir. NT into D.
Yeah, so solid length of spring is equal to NT into D. NT we have calculated as 10, small d as 7, so here you will have 70 mm as your solid length of spring, right? Now one more thing, here you have to assume, that is the gap between adjacent coil, right? So assuming 1 mm gap between adjacent coils. So if you assume this 1 mm gap, then what will be the total gap? That also we have seen. How can you calculate total gap?
NT minus 1 into gap.
Yeah, here it is NT minus 1 into this gap, right? That is 1 mm. NT we have 10. So 10 minus 1 here will give you 9 mm. So now can you tell me the free length? What is free length? Can anyone tell?
109.3.
Okay, it means what we are doing is solid length plus
Plus gap.
total gap plus
Deflection.
deflection, right? So if you go by this, then You are getting it as 100 and
9.34.
yeah, 109.34 mm, right? Or you can consider 110 mm. One more thing they have asked is pitch of coil. So pitch of coil also we have seen, right? How you can calculate pitch of coil. Your free length divided by nt minus 1. Remember, this also we have discussed. So you can consider this actual length what you have received here, right? So this is 109.34 divided by 10 minus 1, that is 9.
12.2.
12 point. Anyone else? Everyone is getting 12.2.
Yes, sir.
Okay, so this is how you can calculate your pitch also. And finally they have asked you to draw this spring that you can draw by yourself, right? Yes.
Yes, sir.
So this is how you can design the spring, right? Now if you go by different questions asked in this gate, then this in gate 2005 they have asked that a weighing machine consists of a 2 kg pan resting on a spring. In this condition, the pan resting on the spring, the length of the spring is 200 mm. When a mass of 20 kg is placed on the pan, the length of the spring becomes 100 mm. For the spring, the undeformed length L0 and the spring constant Kr. So, can you try this one?
Sir,
Yes.
from previous problem, the total gap 1 mm means it was our assumption or given.
Our assumption. It was our assumption.
And in free length, solid length plus total gap. Okay, mean total gap when it is free or when it is compressed.
Sorry?
In a free length equation, we are using total gap term.
Yeah, in free length equation we are using total gap.
And that total gap means when we are considering when it is compressed condition or it is free.
No, see, in case of compressed length, you are considering that gap also. But compressed length is actually your solid length plus that gap. And solid length plus that gap plus deflection is your free length. We have seen, right, this during this terminology of this length. Right, if you see here, this compressed length is nothing but this solid length plus this gap, and free length is this compressed length plus this deflection. It means this solid length plus this gap plus this delta will give you free length. Are you getting?
Yes, means we assume that 1 mm in deflected condition.
Yeah, in this compressed condition we have considered or assumed that this gap is 1 mm between adjacent coil, that we have assumed.
Okay, sir.
Sir, practically compressor length is used, observed.
Theoretically compressed length is this solid length plus total gap, right? This solid length plus total gap will give you compressed length. Okay.
So practically what length we observed under the actual conditions.
Sorry.
Practically which length we observed.
See, generally you will observe this compressed length only when the load is applied, because it will not directly go to this solid length state, right? So in practical application, generally you will find this compressed length only when the load is applied. Okay.
Okay, sir.
Mm. So here if you go to this question, yeah, so can you try this question?
B.
Sorry.
B.
B is, yeah, B is correct. Anyone else got this answer? See, here you are given two different conditions, right? So if you take that load is nothing but that stiffness into deflection, right? Because stiffness is load per unit deflection. So if you take this load is equal to stiffness into deflection, then you are having two different case, right? P1 is equal to this K1 delta 1 and P2 is equal to K2 delta 2, right? P1 and P2 are force, that 2 kg is going to apply this 2 into G, right? mg if we consider. Then K1 and K2 will remain same, right? Because the same spring is there. So K1 is equal to K2, so I can simply write K delta 1 and K delta 2 only. Right, no need to write this K1, K2 because the same spring is experiencing two different forces, right? So K, and in case of this 2 kg force, what happened is your this resting on the length of spring is 200 mm when a mass of so what is happening is in case of this particular 2 kg load, your deflection is L2 minus 0.2, right? 200 mm is mentioned, right? Similarly for 20 kg, sorry, 20 kg, the load is m into g. So here the deflection will be this L0 minus 0.1. So if you solve this equation A and B, you will get this K and L naught.
So P2 is 22 G, no, sir.
It is 22 G, huh?
Yes, sir.
Plus pan mass.
Okay, yeah. Sorry. So here, in case of P2, it is 22 G. Yeah. So if you solve this two equation, then you will find L naught and A. If you take B by A, let us say, then 22 by 2, K will be cancelled. L naught minus 0.2 by, sorry, 0.1, right here, by L naught minus 0.2. So this will give you L naught. Can you tell what is L naught from this? It is 11 L naught minus 2.2 is equal to L naught minus 0.1. So 11 L naught minus L naught is 10 L naught is equal to 2.2 minus 0.1, that is 2.1, right? Like that you will get, yes or no? So you will get 2.1 by 10, so that is 0.21, but it is in meters, so when you convert it you will get 210 mm. Yes or no? Hello?
Yes, sir.
So once you put this L naught as 0.21 here, then 0.21 minus 0.2, if you put it in A, L is equal to 0.21, then you will get this 2G is equal to K, 0.21 minus 0.2, 0.01. So from this you will get K. Correct?
Yes, sir.
So K is equal to 2 divided
One.
by 2 divided by 0.01 is 200. into 9.81. Yes, correct.
Yes, sir.
So this will give you 1960 Newton meter. This is how you will get this B. So everyone is getting this?
Yep. Yes, sir.
Okay. Now next is from 2008. A compression spring is made of a music wire of 2 mm diameter having a shear strength and shear modulus of 800 megapascal and 80 GPa respectively. The mean coil diameter is 20 mm, free length is 40 mm and the number of active coil is 10. If the mean coil diameter is reduced to 10 mm, the stiffness of the spring is approximately. So this is very easy question, right? You just need to find how the stiffness is varying with respect to the coil diameter or mean coil diameter. So first, do you recall the stiffness equation? Anyone? Anyone recall the stiffness equation?
GD power 4 by
GD raised to 4 upon,
8 D cube N.
right? So what you need to check here is what they are asking is if the mean coil diameter is reduced to 10 mm. Previously it was mean coil diameter was 20 mm, right? So what will happen to stiffness, right? So if you consider K1 and K2, then how it is varying with respect to this coil diameter? It is having this inverse and cube proportional, right? Means it is proportional to the inverse cube of this mean coil diameter, correct? So K1 by
Increased
K2,
by 8 times, sir.
yeah, K1 by K2 can be given by D2 by D1 cube. Yes or no?
Yes, sir.
So you have
Yes, sir.
both the diameter, right? D2 and D1.
Hmm.
So D2 is 10 and D1 is 20. So the
Okay.
stiffness of the
Hmm.
spring is approximately increased by 8 time, right?
8. Yes,
So
I
if you,
told wrong. I told
yeah,
decreased here.
it will increase because K2 is equal to this 10 by 20 cube. So once you simplify this, then what you will get, K1 by K2 is equal to 1 by 8, means K2 is 8 times K1. So it is increased by 8 times. Yes or no? Correct?
Yes, sir. Mhm.
So here this one is your answer. So everyone is getting this?
Yes, sir.
Okay. Next is this. The spring constant of a helical spring does not depend on. So can you tell this one how you are going to address this particular question?
Material strength.
Sorry? Huh, correct, because coil diameter, number of active turns and wire diameter is going to affect. So material strength is the correct answer. Okay,
Sir, but G is there in expression.
so G is what is G?
It is a modulus of rigidity.
Right, so that is why this strength is not affecting this particular spring constant, right?
But it is also depend on material.
Yeah, but here material strength, it means I guess that particular young modulus they are discussing about, I guess. Right. Sorry, actually, yeah, correct. This is how we need to consider. Okay, still I will check, right? Okay,
Okay, sir.
yeah. Okay, now the next is from GATE 2017. A helical compression spring made of a wire of circular cross section is subjected to a compressive load. The maximum shear stress induced in the cross section of the wire is 24 megapascal. For the same compressive load, if both wire diameter and the mean coil diameter are doubled, the maximum shear stress induced in the cross section of the wire is. This you can do, I guess, by yourself. Can you calculate and let me know what you are getting? Hello?
Yes, sir. Doing six, sir.
Yes. Anyone else? Anyone
Yes, yes,
else got the answers? S6?
yes, sir.
How you have calculated? First you have to have idea about this tau max, right? How you can represent this tau max? We have written it as 8 PD upon pi d cube into k, something like that, right? Yes or
Yes,
no?
sir.
Yeah.
Yes, sir. Mm-hmm.
So further you can consider it as 8 pc upon pi d square, let us say, because c is capital D by d, right? So here your
Mm-hmm.
tau is inversely proportional to the square of the coil diameter. So
Coil diameter.
basically your tau 1 by tau 2 is equal to d2 by d1 square. Is it correct?
Mm. Uh-huh.
So what they are asking is tau 1 is given as 24, huh? You need to calculate tau 2, right? And your,
Yes, sir.
yeah, so what they told is you need to uh, double the diameter, right? So your 2d by d square, correct? So once you solve
Mm.
this, your tau 2 will be 6 because this d will cancel out, right? And you will have this 24 by 4. So it is 6 megapascal. Yes or no?
Sir, here both diameters are
Yes.
going to double. That's why C is same.
Yeah. Otherwise you cannot reduce it to this form, right?
Yes,
Hmm. If this capital D and small d are going to vary differently, then you cannot directly consider this C here. You have to keep it separate, right? Okay. So the next is, if the wire diameter of a compressive helical spring is increased by 2%, the change in spring stiffness in percentage. You can calculate this, I guess. First you have to have idea that how this spring stiffness is related to your wire diameter. 6 GD raised to 4 upon this 8D cube or 8P cube, and this is what it is, right? Sorry, 8D cube, capital D. P is our load, right? So this is how your stiffness varies. Correct? Yes or no?
Yes, sir.
So now, as from this you can write that K is proportional to D raised to 4. What they have asked is, they have asked to increase the wire diameter by 2%. So if you go K1 by K2, then here if it is D, then in case of this 2 it is 1.02 D. Yes or no? Yes or no?
Oh, no, sir.
Sorry?
Power 4.
Oh, sorry.
Yes.
Here power is 4, yes. So now from this you will find how K2 is. Then K2 is
Hmm.
1.02 to the power
2 to
4
the power 4.
into K1, correct?
Yes, sir.
Hmm.
So your K2 is equal to what you are getting if you go for power 4, 1.082 something,
242.
right?
Yes, sir.
242. Yes. 1.08242.
Okay, right. So this is your K2. Now percentage increase in stiffness they have asked, right?
8.242.
Percentage increase in stiffness. So that will be equal to K2 minus
Minus
K1
K1.
upon K1 into 100, right? So you will get it in
Yes.
percentage. So it will be
8.242 percentage.
okay, minus 1 I am writing, right? Taking K1 as constant or common. So it is 8.242%, right? Almost. Okay, so everyone is getting same?
Yes, sir.
Okay. So if you go for the next one, a helical spring has a spring constant K if the wire diameter, spring diameter and the number of coils are all doubled, then the spring constant of the new spring becomes, you can calculate this I guess, this spring constant is nothing but this GD raised to 4 upon 8D cube. And now what they are asking is
Option B.
option B. Yeah, correct. What they are asking is wire diameter, coil diameter and the number of coil all are doubled, right? So for that new K, your this wire diameter is doubled, then this coil diameter is doubled and number of coils are doubled. So basically this 2 to the power 3 into 2 will be 2 to the power 4, and here also 2 to the power 4, so it will be ultimately equal to same K, right? Because all will get cancelled. That is why you are getting this D, correct? Okay.
Yes.
So now if we go for the next one, here the shear stress distribution on the cross section of the coil wire in a helical compression spring is shown in the figure. The shear stress distribution represents direct shear stress in the coil wire cross section, torsional shear stress in the coil wire cross section, combined direct shear and torsional shear stress in the coil wire, or combined direct shear and torsional shear stress along with the effect of stress concentration at inside edge of the coil wire cross section. So I guess we have discussed this, right? What we have discussed in the earlier case while deriving this shear stress, if you remember, we have considered direct shear stress and torsional shear stress. Yes or no?
Yes.
Yes, sir.
Yes.
So the C will be the answer, right? Combined direct shear and torsional shear stress in the coil wire cross section. Okay.